Hello, this is my presentation for Physics 2212's Lab 4, Circuits. The purpose of this lab was to use the principles of energy and current conservation to predict the behaviors of circuits, use multimeters to measure actual values of current and potential differences, and to examine the behavior of ohmic resistors and capacitors. An overview of the results are that in Part 2 the current was measured to be 0.02 amps, and in Part 3 of the lab, our computed RC value was approximately 6 seconds. Some of the principles/concepts we used were the circuit rules, more specifically the loop rule, which says delta V equals 0, and the node rule, which says current in equals current out. We also use Ohm's law, which is voltage equals current times resistance, energy and charge conservations, series versus parallel circuit setups, and steady state. An assumption we can make is that wires and ammeters in the simulation contain zero resistance. For the first part of Part 2, we have that our circuit is the system and everything else is the surroundings. Our circuit consists of two 1.5 volt batteries, which can also be modeled as one 3 volt battery, one 47 ohm resistor, and one 100 ohm resistor, in addition to wires and ammeters. To predict the current at the two locations, we can solve for the current like shown. Since the circuit is in series, all the currents are equal, so that means current 1 equals current 2, which equals 0.02 amps. This matches the readings we are given by the program. We can also observe that if you flip the ammeter, you get the same current magnitude reading, but in the opposite direction. For the next part of Part 2, we replaced one of the ammeters with a voltmeter. This caused our ammeter to read 0 amps because adding the voltmeter opens the circuit. If a circuit is open, no current can flow, causing all the voltage to pool on one side, so the potential difference across the voltmeter is the total voltage in this particular series, which is 3 volts. Reading the voltage at different points in the circuit led to different voltages noted. However, like expected as stated by the loop rule, delta V across the entire circuit is 0 volts regardless of there being different readings at different locations. We can also see that current does not change because the voltmeter has high resistance, therefore current does not flow, not altering the ammeter reading that we got before, which was 0. Now putting the 100 ohm resistor in parallel to one ammeter, we see that there is a change in the current reading. Current wants to take the path of least resistance, so since the ammeter has 0 resistance, the current increases since it can't go through the circuit, since it can go through the circuit in a more efficient manner. Given our potential difference readings done in Part 5 and 6 of Part 2, we can calculate the resistance in the following elements of the circuit: the 47 ohm resistor, 100 ohm resistor, the wires, and the ammeter, as shown on screen. For Part 3 of this experiment, we are now looking at a setup consisting of batteries, wire, capacitor, and a bulb at varying resistances. We notice that while the capacitor is charging, the bulb begins bright and then dims out as the capacitor fills. A very similar thing occurs when the capacitor is discharging. We see that the 10 ohm bulb setup charges in 5.72 seconds and discharges in 5.91 seconds, while the 20 ohm bulb charges in 11.11 seconds and discharges in 10.72 seconds. For the last part of our experiment, we looked at how voltage of the circuit changed after 20 seconds. Measuring the voltage across the capacitor as it was discharging about every second, we noticed an exponential decrease in volts as time progressed, the chart on the left. Taking that information, we can find the time constant of our circuit by taking the natural log of the graph on the left to get the graph on the right. From there, we can use the slope to solve for the time constant. Our experiment RC is 6.02 seconds, while the expected RC is 6 seconds, done by multiplying the resistance of the bulb by the capacitance of the capacitor. Our two numbers are very similar, which leads us to conclude that our experimental method is pretty accurate. For the first discussion question, a real-life ammeter has some resistance, so our current would most likely read slightly lower than the ideal setup of the simulation. For the second question, If there was no resistor, the capacitor would charge almost immediately. In real life, it would take some time to charge because real wires have some level of resistance, but not as much as an actual resistor. And finally, because we used a simulation, the only errors that may have been occurring were most likely in the misunderstanding of directions or the misuse of the program itself, rather than the error in the circuit or the charge/electron movements.